from the sigma algebra generated by this A naught 2. Right. So this is going to be a measure. Right. So you can extend it via what is known as outer measures. With the help of outer measure, then you can do this, right? And then, so if this pair, if the triplet, not the pair, triplet, well, rather than writing it as, if this triplet is sigma finite, then this mu is unique. This is what we saw, right? So a natural question is, do we have an example? Of course, we have a simple example. What is known as R, Borel sigma algebra, and then the Lebesgue measure. Is this the only example do we have? If this is the only example, then what is the point for doing all these abstract? Right. So now what is our aim? We are going to produce a large class of examples. Right. So let's begin with. Right. Proposition. Let f from R to R be increasing and right continuous. If, well, open AJ, closed BJ, 1 less than or equal to J less than or equal to N, or disjoint half open intervals let me define mu naught of the union J running from 1 to N AJ BJ as summation J running from 1 to N. Can you guess what it is going to be? Just a guess. Well, in the case of
BJ minus AJ.
BJ minus AJ, if you are expecting a Lebesgue measure. If you write it as BJ minus AJ, what you are going to get is only the Lebesgue measure, right? Because if you start with the length, then what will you end up with? What will you end up with? Lebesgue measure. But we want something which generalizes the notion of length. So how to get that? How to get that? How to make use of this F? What is the role played by this F? Well, what is length? Well, how do you define the length? Length of an interval is Bj minus Aj. if I choose f of x equal to x, then what is this bj minus aj? If I choose fx as x, then bj minus aj equal to
fbj minus faj.
f of bj minus f at aj, right? So now what will be the candidate here? Summation j running from 1 to n yes, summation j running from 1 to n, well, it is f of bj minus f at aj. And let mu naught of phi equal to 0. Then this mu naught is a pre-measure on the algebra generated by the collection of all, well, I'll simply say generated by S, which is half open interval. Correct. In fact, so you can notice that this algebra coincides with the collection of all sets which are finite unions of half open intervals. In fact, finite disjoint unions of half open intervals. Right. Well, let me just make a remark, same thing, whatever I said that. So note that the algebra generated by S coincides with the algebra of all sets of the form which are of the form sets which are finite disjoint unions of half open intervals. Correct. Right? Proof. Now let's get into the proof. Yes, so what are those things that we'll have to prove? What are those things that we'll have to show?
If An is a sequence of disjoint sets such that their union belonging to A naught, then mu of union equal to summation of mu A.
Before that, is mu naught well defined? First question, is mu naught well defined? See, I have taken a union j running from 1 to n, aj, bj. I see it can very well happen that union I running from 1 to n, aj, bj can be same as union, maybe I'll put it I running from 1 to m, ci, di. This can happen. In that case, how do you show that mu naught of these two are one and the same? We need them to be one and the same. Only then it is well defined. That's what is well defined, right? So first thing that we will have to show is that this mu naught is well defined. So first claim, mu naught is well defined. Right. So let aj, bj, j running from 1 to n, be a disjoint family. And let union j running from 1 to n. So suppose that aj, bj, so if this union is same as some half open interval ab, so then, so now what you can do is you can relabel the index. After relabeling the index, we can assume that A is nothing but your A1, which is less than B1, which is equal to A2, which is less than B2, A3, which is less than Bn minus 1, which is An, which is less than Bn, and that's exactly your B. Right? So just relabel the index and then you can assume this fine. So therefore, summation j running from 1 to n, f of bj minus f at aj. What will be this one? What will be this one? What will be this one? What is f at aj?
B minus A.
B minus A.
F
B
of
minus
bj minus 1.
FP minus FA.
It is only FB minus FA. Only the first term and the last term will survive. All other terms will get cancelled. So it is FB minus FA. So if you want, so you can notice that leave the first term and then starting from the second term. So note that this is same as 1 to n f of bj minus f at aj. Write down the first term, which is f at b1 minus f at a1, and then the remaining terms, they are going to be summation j running from 2 to n f of bj minus f at b j minus 1. This is what you will have to observe. Once you observe this, then everything follows. Yes. So for j equal to 1, sorry 2, this will be f at b1, which will cancel with this. So f at a1 is exactly a. Yeah, so that's what you'll have to realize. Fine. Fine. So what we have shown is that, well, what happens in the case when the union is just an interval, right? So what does it tell us? What does it tell us? First thing. So it tells us that if the union is a half open interval, then mu naught depends only on the endpoints. It doesn't depend on how you split it. Right? So thus, if the union is again a half open interval, then mu naught of that interval coincides, that interval depends only on the endpoints. And so, which means that it doesn't depend on how this disjoint union is chosen. Right. So, which means on the half open interval, this mu naught is well defined. That means on the half open intervals, mu naught is well defined. Right. The next one that we wanted is what happens if it is an arbitrary union, right? Now, let I running from 1 to n and j running from 1 to m be two finite sequences of disjoint half open intervals such that union I running from 1 to n I is equal to union j running from 1 to m jj. Correct. Right. Now, note that this is, again, we have been doing all these things without our knowledge, all these things. 1 to n I, which is same as union I running from 1 to n This II, I can write it as union J running from 1 to M, II intersection with JJ. And therefore now this is same as again union. So I can even split it so that J running from 1 to M. I can rewrite the whole thing and get this one. Right. So these two are fine. Therefore, so once we have observed this, now summation 1 to N mu naught of JJ. Well, how do you start? Mu naught of II because it is 1. So mu naught of II. So one could have chosen it as the endpoint, using the endpoint, but doesn't matter here. Why? Because this mu naught is well defined on the half open intervals. Therefore, this makes sense. Right. Which is same as summation 1 to N mu naught of II is union J running from 1 to M II intersection IJ. Right. But then if you use the definition of mu naught, this is going to be 1 to N summation 1 to M mu naught of II intersection Ij. Right. Now being finite sum, I can just interchange the summations. So 1 to M. I am not writing the index, but please be careful with the index. II intersection with Ij, right? Now, which is same as, let me repeat the same steps, whatever we did in the beginning, which is again mu naught of Jj, and this is, and that's exactly what we wanted. Well, rather than writing it as just this one, let me write one more. Mu naught of union I running from 1 to N II intersection with Jj. And that will give rise to 1 to M mu naught of Jj. That's it done. So which tells us, what does it tell us? Which tells us that mu naught is well defined. Right. Yes, we have shown that mu naught is well defined. Yes, next thing what you'll have to show is that it's a measure. It's a pre-measure. This mu naught is a pre-measure. Right. So what was our fundamental assumption? Yes, so we assume that mu naught of empty is 0. So it's enough if we can show only the countable additivity part. Whenever the union is there, right, there inside the algebra. So it remains only to show that if n in n is a sequence of disjoint intervals, in fact half open intervals with their union also coming from the algebra A, then mu naught of the union coincides with summation over n in n mu naught of In. Right. So this is what we wanted. So once we can, if we can show this, then we are done. Right. Yes. So first thing. So let in n in n be a sequence of disjoint half open intervals from A such that union over n in n in belongs to A. Right. Fine. So this union belongs to A, and what is A? What is A?
Algebra.
And what are the elements of this algebra? We made a remark.
Finite union of half open intervals.
You can write it as a finite union of half open intervals. Right. So since union over n in n in belongs to A, it can be written as a finite union of half open intervals. Right. So you can write it as a finite union of half open intervals. So what you can do, at most what you can do, so this union, we have now written it as a finite union 1 to m jj, right? Which means that this jj contains a subsequence of intervals from this collection, for a countable collection in, whose union is going to be jj, which means each jj contains a subsequence of intervals from this collection whose union is jj. Right. So thus the sequence or the collection in, the sequence of half open intervals, this can be partitioned because they are disjoint. You can partition them or into finitely many subsequences such that the union of the intervals in each subsequence union of the intervals in each subsequence is again a half open interval. Right. So the way we have defined this mu naught, the definition of mu naught, that itself tells us that it is finitely additive. The definition tells us that it is finitely additive. So by definition, the way we have defined tells us that mu naught is finitely additive. And therefore, so it is finitely additive. So what have we done? We have returned union over n in n in as union j running from 1 to m. Well, how should I write that? Well, union j running from 1 to m, union k running from 1 to, well, union over k in n, maybe that's the right one, over k in n, I k j. So this I k j, for a fixed j, it's a subsequence of in. Right? And this union, such that this union is again a half open interval. So let's say jj. This is what we have been assuming. And therefore, if you want mu naught of this thing, whole thing, union over n in n, in, then this is going to be mu naught of this finite union right? And each one of them, well, I could have written it as union over j running from 1 to m. This is jj. And using the fact that it is finitely additive, this is same as union over j, sorry, summation. J running from 1 to m, mu naught of jj, right? But this is same as j running from 1 to m, mu naught of the union over k in n, ikj. So, in order to prove this statement, well, I'll call this 1. In order to prove this, we can, without loss of generality, assume that this union is a half open interval because of all these arguments. Right? So, right. And therefore, well, let me erase this part. Well, so as mentioned above, union n over n in n, in is equal to this. Therefore, we have this one. Therefore, we can, without loss of generality, assume that because see, the ins are disjoint, and therefore all these ikjs are also going to be disjoint, and therefore all these make sense. Fine. So we can, without loss of generality, assume that union over n in n, In is again a half open interval. Right. So let union over n in n, In, let me call it as A comma B. Right. So now what are we supposed to prove? What are we supposed to prove? What are we supposed to show now? We will have to show that mu naught of union over n in n, In is equal to Fb minus Fa. If we can show this, then we are done. Is it clear for all? Everyone? Is it clear?
Yes, sir.
Okay, fine. At least there is one to respond. Thank you. So once you have assumed this one, then mu naught of this interval AB, yes, which is going to be, so let me write it as a union I running from 1 to n In, I union with this AB minus this union I running from 1 to n II. So I have split it into two parts. Now, first one is from the algebra, second one is also from the algebra, and therefore I can now use the subadditivity, sorry, additivity, finitely additiveness. So this is same as I running from 1 to n II plus mu naught of AB minus this union I running from 1 to n II. Right. So mu naught is always a positive quantity, therefore this is bigger than or equal to mu naught of the union I running from 1 to n II. And again, II's are disjoint and mu naught is finitely additive, therefore this is same as summation I running from 1 to n mu naught of II, and this is true for all n in n. As usual, letting n tend to infinity, what do we get? Mu naught of the interval AB is bigger than or equal to summation I running from 1 to n mu naught of II. Yes. So what is that is left to prove is the reverse inequality. Yes. So yes. So we'll prove this in the next class, that is on Friday. Right. Fine. Yeah. So that involves two cases, two or three. Case one. That involves two cases. In fact, there are three cases. There are three cases. Fine. Once we have done that, then we should be able to state the main theorem in the next class.
Infinity.
Huh?
Summation 1 to infinity.
Yes. Thank you. Yeah, because you have let n to be infinity. Thank you. Right. Right. So if you have got any questions, please.
Sir, why